Hello everybody, welcome to the screencast. Now I want to show you how to create a language in MPS. Obviously the scale of languages that you can create with MPS is pretty wide, and we are at the beginning of the journey of learning MPS, so we'll start with a very simplistic language. Using a simple language for our demonstration gives us the advantage of going slowly over the core principles and then gradually increase the complexity of the languages that you design in the following tutorials and exercises. We're going to use one of the sample projects that are bundled with MPS. It's part of the It's a sample Java extensions project, part of which is a constants language, and that is the language that we're going to create ourselves here. You see from the structure the language is very simple. It only has 3 concepts, and we will start with the 2 most important ones in our exercise here. But ultimately we'll get a language that allows you to define constants. Each constant has a name and a value. Ideally the value is an expression, but we'll get to that gradually. We'll start with simple plain values. And now this language allows you to define constants and then have them generated into Java. And the generated Java class then contains for each constant a public static final field that then you might use in plain Java code as constants. Okay, but we'll start from scratch. So we need to create a new project. It will be a language project with a sandbox. So when you're starting a new project, you pick the option you want. Typically you want to design a language and you want to test that language right away in some sort of solution called sandbox solution. So you check that. You give the language a name. Constants is a good name, and you name the project as well. So here we have it, an empty project with a language which is empty at the moment, and a solution, sandbox solution for that language, which also doesn't have anything in it. Okay, before we start, let's set the terminology right. Now the yellow guy is a language. So all the yellow nodes here are languages, and then they contain models for each aspects of that language. If you define a language, you have to define what structure it has, what editors should be used for editing the language. There might be some constraints, some functionality associated with nodes, and so on and so forth. And the orange nodes are solutions, so basically places where you write code, and you can always decide what languages you use to write your code. And this is done through dependencies. So if you open the properties of a solution, now you might select the languages you want to use in that solution. Notice we here are using constants. That's the language that we design as part of this project. Okay, time to start the tour. So, if you remember correctly, the language contained a set of constants and then one constant on each line inside this set of constants. Now, to represent a language like this, we need 2 concepts. One concept would represent the whole set of constants, and the other concept would represent each individual constant. The first place where you typically go when you design a language is the structure, because this is the place where you design the concepts out of which the AST, the model, will be constructed. So the allowed kinds of nodes that can be part of your AST. So first, we need a concept for constants. It's going to be a base concept. That's like the common super concept of all concepts. You see, in MPS you design your language in an object-oriented way. So you design your structure by defining concepts. And concepts, you can think of them as Java or other classes that extend one another and can implement some concept interfaces. So in our case, constants is something that represents a set of constants, and it needs to have a name. So normally we would add a name property of type string here. So now we have a set of constants and it has a name, a string. However, for a name, we typically want some special treatment from MPS, so that MPS knows, hey, this is the name that I should display whenever I see a node of this concept in the left-hand panel, for example. So instead of defining the property ourselves, we'll just implement it. We'll take iNamedConcept, which is an interface that already has a name property and some additional behavior and refactorings associated. So we'll just take the name property from here by inheriting it from iNamedConcept. Additionally, we want constants to be at the root of the AST. Constants won't be nested under another concept, but they will be only listed here directly under the model in the program. So they will be root. So they will be root concepts, and we might give it an alias, a string that will be used to represent this concept in the completion menu. So to easily distinguish this concept and to nicely represent it in the completion menu, this alias can be defined. So that is constants, and now underneath constants, we want to have the individual constants. We can call it list of constants, and these will be of concept constant, which we don't have yet, so we'll create one. So a new concept called constant, and each constant has to have a name and a value. So for name, we're going to use iNamedConcept. Now we can give a nice alias here. It's no longer this one won't be a root concept because it will always be nested underneath the constants concept, and we'll have 0 to n of constants in each list of constants. And each constant has a name and also a value. And for now, let's make value a string. So now we have constants, which contains constants, and each constant has a name and a value. So now we can rebuild. Notice I right-clicked on the language and picked rebuild. That rebuilt the language, so now the language is ready to be used in our solution. So when I go to the solution, the code inside solution is organized into models. I pick the model that has been prepared for me, but I could create more models if I wanted. New model here would do it. So I'll use this model, and in the model I create a new root concept, and the language I'm importing only defines one root concept, and that is our set of constants, this one. So I create one, and now I can work with it. So I've got a default presentation of that concept on the screen because I haven't customized the visual representation of the concept on the screen just yet. So now I'm prompted to provide the name. My constants is a good enough name. And now here's the list of constants that I can create inside this list of constants. So if I hit enter, now I get a new empty constant ready. So I can give it some name and a value. And I can hit enter again. And I can provide another name and value. So far, so good. Now, the next step typically you do when you design a language is to customize the visual appearance. This means we need to define the editors for our concepts. So back to constants, and we create a new editor. And in the editor now we lay out the properties and children of a concept. We need to lay out them somehow on the screen. So in the editor we use a dedicated language that is available for defining the layout. Typically we start with the indent layout, which is square bracket and minus, a shorthand for it. So now we have the indent layout, so all components will be laid out on the screen in a text-like sort of layout until you hit the end of the line, and then you'll jump on a new line. You could easily pick a layout that lays out components vertically or horizontally or in a table arrangement. But for our purpose, this is good enough. So on the first line at the top, we would like to put out some keyword. Let's say list of constants. And now next to it, we would like to put the name of the list of constants. Remember, this editor is defined for constants. Constants has a name property coming from the iname concept, so it has a name, and it has a list of constants. So these are the two items we need to lay out on the screen. So we do a constant cell. Now here's a trick that may be very useful. Alt 2 or Command 2 will open an inspector window. And in the inspector window, you can always specify additional properties, additional qualities of a cell that you select in the main editor. So if I click on this cell here, the cell that represents this constant string, the keyword that people won't be able to change on the screen. So we see here it's a constant. It's mentioned up here. And then I can customize it by, for example, assigning a style named keyword to it. So it will be colored differently and perhaps displayed in bold. Now here I want to have a name. Then we would like to put a new line break. And on the new line, we would like to start listing all the constants. Perhaps we should include one empty line there. So I select a constant cell. So now we will have an empty cell. Again, a new line. And on the next line, we'll just start adding the constants. So we pick the list of constants. So that's the child. So all the constants will be now displayed here. And now the collection, however, should be ordered vertically. So in the inspector, we change the order of the constants to be vertical. So I hit compile, and now switching to my constants, now I see the editor has been changed. Now it has this list of constants here. Now here's the name that I can change. So this is editable cell. This one is obviously not editable. I can't change that. So the next step is to customize the editor for these individual constants. So I go to the constant concept. Each constant has a name, again coming from iname concept, and a value, a property of type string. So we need to visualize those somehow. So we create a new editor. Again, I use the indent layout. Let's prepend each constant with some text, like my constant. And again, we could have it a keyword. So now we have a keyword, my constant. Now enter. So I get a new cell. That cell should hold a name property. Now we could have a colon. And now we could have the value property. Now if we rebuild the language and look back at the code, we see that now the updated editor is being used. So we've got a list of constants, and now for each constant we have a cell. If I hit enter, I've got a new empty constant. And I can add more constants. Well, we're not really benefiting from the indent layout in constants. Maybe we should. So now, going to the list of constants, we could slightly indent it. You could either hit Alt-Enter and type indent. All these actions in the Alt-Enter menu are called intentions. These are like quick, minor refactorings of the code that you're looking at. So we could add an indent, and now, you know, the collection is being indented. Alternatively, or you might have noticed the automatic process here edit this property into the style. So that's the other way of indenting this. We could go down here directly, hit Control Space, and now we see all the styling options that we have to customize the cell. In our case, we could pick indent, layout, indent, and this has the meaning of indenting a piece of code. Just like the new line that we added here with Alt-Enter resulted in this indent layout new line property being set to true on this particular cell. Okay, so now we have this language, but it doesn't really do anything useful. We can't hit compile and have Java generated out of it. We have to do an extra work to encode the semantics of this piece of code by creating a generator, and the generator will then be invoked to translate this code into, well, the target code. In our case, it will be a Java class. For each set of constants, we'll get a Java class, and in that class we'll have a public static final field for each of these constants. Before we start with the generator, there's a few things you need to know. First of all, from MPS, from this example, we are generating some Java source, so .java file, a text file. Now in MPS, we've created a long time ago a copy of Java called MPS base language. It's a one-to-one copy of Java, but projectional, so that you can use projectional editor and do all the fancy tricks that MPS can do to edit your code. And then this base language can be translated into Java source through text generation. So there's a model to text generation, which takes your model, if it's written in pure base language, and generates a set of .java files out of it. Now, on top of this base language, then, you may define extensions or applications that use extra constructs which are not part of base language, like closures, date and time, collection API, or are constants. And these constants get translated into MPS base language first, and then this base language will be translated into plain Java. So it's important to distinguish two phases in the generator. First, it's a model-to-model transformation, where you take an AST and transform it into another AST gradually. So in several stages, the AST gets modified until you get an AST that only contains base language concepts. And these are then easily transformed into plain text. And we don't need to bother with that phase. What we need to define is how to translate our constants into a plain base language. And we do that through templates. So if you've got on the left hand side, you've got an AST that contains something that is not part of pure Java, you define rules that will translate that stuff into an AST that contains pure Java. So you use these templates that define the generated Java code, and in them you use macros that take values from the input model and put them into the generated code. So now you go down to the generator. In the generator, this is a module called generator, and it has at least one generator model. And in the model, there's already one entry, one root node called mapping configuration. And it contains the rules to use to generate your code. So the place where we will start is the root mapping rule. This is the place where you define how a root concept of your language gets translated into typically a root concept of the target language. So I hit enter. Now pick constants, which is our root concept. And now we need a template that will be used for the translation. So we hit Alt Enter, create new root template. And now the target concept will be class, because we are generating a Java class. So we pick now what we are generating. We're generating a Java class. If we hit Control B, we get to the template itself. So here's the template. It's a template that will accept constants, a node of concept constants, and it will turn it into this Java class. Well, let's try what happens. So if we do rebuild the language, now we go to my code and hit preview generated text, which will basically take this language and translate it into Java. Now this is what gets generated. A class called map constants, which is empty. So it's exactly what we specify here. So in the template we specify what should be generated, well, and we get it. So now if we make changes to it, then we get different class generated. Well, we want to make changes to the class that would reflect what is written in our code. So first of all, we would like to have a different name of the generated class, because our list of constants is called myConstants. So we would like this class to be also called myConstants. but when you define this template, you don't know what the name of the constants will be. So you have to somehow customize the name using the input that you get in the generator. You know, the generator takes this code and translates it into some Java class. So it can now take elements from the input and put them somewhere in the generated class. And this is done through macros. There are different types of macros. We'll use at least a few of them here in our example. So the first one you should get familiar with is the property macro. Now I will visualize the AST here. So we've got a Java class, and the Java class has a property name which is called mapConstants. That is why we see mapConstants here. Remember, this is not a textual template, this is projectional template. So this is not text generated, this is not generating text, but we are transforming models. We are transforming one model into another. So the generated class here has its name stored in a name property. And now we want to generate a class, but we want the name property of the generated class to be different. So we put a property macro on this class that will do that. That will replace the name that you see here with the name that we get from the input model, from the node. So node, the parameter, is of concept constants. Obviously, because that is what we say up here. So we've got a node which is constants, and constants have a name, right? The constants concept has a name coming from I-named concept, this name. So in the generator, in the property macro, we take that name and replace the name of the class, the map constants, with this new one. So now when we rebuild the language and look at the generated code, we get a class which is called myConstants, just as we say here. Well, the next thing we want is to have static fields for each constant. So we want to have a public, static, final, let's say string, field, initialized to some value. So I compile, we'll look at what gets generated now. Good, so we get a field, but obviously this field doesn't reflect the actual constants we have here. So we need to do that somehow. So back to the template, and we'll use a loop macro. So we select the whole line, including the semicolon. So now we see we've selected a static field declaration, because we want to generate static field declarations. Again, Alt-Enter. And now we pick a node macro. Or we can use a shorthand, this loop here. But we'll walk the whole way. So node macro here, loop. So we pick a loop macro, and now we say what we should loop over. So the thing is, our node, which is constants, the node has a list of constants. So we need to loop through them, and for each constant we generate a static field. So we go to node dot list of constants. Here we go. This is this guy. So we iterate through a list of constants, and for each we generate a public static final field. Okay, let's check what we get generated now from our code here. Okay, now we have 3 fields, one for each constant, but they are the same. They still have the field name and the value. So we need to change those as well. So again, if I highlight static field declaration, and if I visualize in the AST view, I see that there's a property called name on the field. that contains the value field. So I need to change that property with the name of the constant. So I go to the field and say that I want to assign a property macro here that would replace field with node. But what is the node here? The node is now an individual constant. Since we are inside a loop macro, the loop macro iterates through all the constants, and for each constant it invokes the code inside. So inside here, the node, the current node, is the constant, not the whole list of constants. So we pick the name of that individual constant. I recompile, and now we see the effect. The fields are now named differently. We need to do the same for values now. Now, since values at the moment are properties, we do the same thing we did for name. So we'll just take whatever's inside the quotes and use a property macro for node.value. Now we use the shorthand. So you see we have a property macro that will replace the value of that string with a value of the constant. I recompile. We go back here, and here's the generated class. Now the name is customized, the names of the fields are customized, and the values reflect the values in the original code. So our work here is done. Okay, that is our first language we've created in MPS. I hope you enjoyed it. Thanks for watching. Goodbye.